Okay, we're going to take a look now at June 2004 paper pH6 A23 June 2004. This question is very similar to a question which has come up subsequently, which asks about the difference between a cyclotron and a synchrotron. Essentially, you will need to know how those two operate and what the differences between them are. So first of all, describe the principle of operation of the synchrotron. So a synchrotron has particles moving around in a fixed radius orbit. Okay, so in a fixed radius circle. In order to maintain that fixed radius, the strength of the magnetic field has to be adjusted, has to increase. As the particles go around that fixed radius, okay, held in there by the magnetic field, they're accelerated at the gaps by a radio frequency electric field. So the electrodes change from positive to negative in a synchronized way in order to accelerate them. The frequency then of that field has to be adjusted to ensure that the particles are always accelerated at the gaps. Alright, so we're looking for 5 points here, so we're probably looking for 4 marks in the description of what's happening. So first point I would say is that the particles travel in a fixed radius circle. Okay. Second point then is that the strength of the deflecting magnetic field increases to maintain this. Okay, so it has to increase to maintain that. Then the particles are accelerated at gaps by the electric field, and that's a radio frequency E field that's produced. And the final thing is then that the frequency of the alternating voltage is changed to ensure particles are always accelerated at the gap. Okay, then the difference between the two is in the synchrotron we have a fixed radius. The cyclotron, it increases. Don't leave you a lot of room to answer these questions, but I suppose you have to make the best of it. And also in a synchrotron, the B field increases. The cyclotron is constant. Right, and somewhere in those you'll find your 5 marks for that. Particle accelerators are tended to use quite often to accelerate particle and antiparticle, and here we're given that they produce a pair of gamma photons. And remember, it's an annihilation reaction and it produces gamma photons. That's what happens in that annihilation reaction. So we use Einstein's mass energy relation to calculate the minimum energy of each photon. Right, so what we're saying here is that the minimum energy that's available is going to be equal to, well, the energy is equal to mc squared, so E equals mc squared according to Einstein, but because we produce 2 photons of that, then that means that it's 2 times mc squared is the total energy available. The minimum energy of each photon. But because we're producing two photons, then it's mc squared that we're looking for. So we have 2 times the energy is equal to 2 times mc squared, which is equal to 2 times 9.1 times 10 to the minus 31 for the mass of an electron times the speed of light squared, so that's 3 times 10 to the 8 squared. And whenever we work that out, then that gives E is equal to 8.19 times 10 to the minus 14 joules. Calculation isn't over because that's in joules, and we need to calculate that then in electron volts, so that's 8.19 times 10 to the minus 14 divided by 1.6 times 10 to the minus 19, and that will give us what it is in electron volts. Then we need to change that to kilo electron volts, and when you do that, what we find is that it's 512 kilo electron volts. The minimum frequency of the gamma radiation, well, here we're going to use E equals HF. Right? For the photon, the energy is equal to Planck's constant times F, therefore F is going to be equal to the energy divided by Planck's constant, so that means it's equal to 8.19 times 10 to the minus 14 that we'd calculated above, and that's going to be divided by Planck's constant, which is 6.64 times 10 to the minus 34. That means then that the frequency is equal to 1.2 times 10 to the 20 Hertz. And that's the end of that particular question.